Hey everyone, today we're starting section 1.3, which is describing functions. Today we're going to be looking at the domain and range part of it. Describing or investigating functions is something we're going to do all year. So this is just kind of the intro, but it's something we're going to constantly do. And some of the characteristics that you're going to be looking for are x and y intercepts, which I know you've seen before. Domain and range, which we're going to learn today. And then in the next couple of days we'll learn about mins and maxes, intervals of increasing and decreasing, and our end behavior. So today again is our domain and range. So first we'll start out with some definitions. Domain is just the set of inputs or the x values for a equation or graph or representation. Okay, so domain is x, and range is the set of outputs or the y values. So the way I remember it, D comes before R in the alphabet, X comes before Y in the alphabet, so domain is your X and range is your Y. The way we write domain ranges, it depends on the representation we're given. So if we're given a representation such as an ordered pair, those are pretty easy because domain is the set of inputs, so we just write the X values. So make sure you do write x equals because we're going to know that domain is your x's, and then we write our x values that are there. So our x here is -3, 3, and 4. So now even though we have the x value 4 twice, we don't have to write it because we already have it once. And domain is just your set of inputs. So if you wrote 4 again, that's just being redundant and extra work you don't need. 4 is that, or we already wrote that 4 is in the set of inputs. And then our range, similar. Now it's our y value, so we just want to make sure we put y equals in there. And then we have our y values of -1, 3, and 4. Again, we have -1 twice, but we don't have to write that twice. Always try to also write them from smallest to largest, as I have here. All right, we also have mapping diagrams that we look at from time to time. And so in our mapping diagram, it's a very similar to like a table. We have inputs on this side, outputs on that side, and it just arrows to the next input to output. So in this case, here are our inputs. You can see that they are 0, 2, and 5. There's no other inputs, so we're going to write it just like we did up here, x equals 0, 2, and 5. And then the ranges, again, we're going to write our outputs. Now, even though it looks like there's 3 outputs, you have to be careful here because there's only arrows pointing to 2 of the outputs, the 4 and 6. There is no arrow pointing to the 3. So therefore, our range is just going to be 4 and 6. And then if we just are given a table, again, it's very similar. We are just writing our inputs. So domain is our input, so we write x equals. Always want to put our smallest first, so -2, -1, and 3. And then our range against our output, so we put y equals, and we'd have -3, 0, and 4. All right, so again, the representations of ordered pairs, mapping diagrams, and tables are fairly straightforward, where you're just writing your x and y values out. We also are going to have domain and ranges of word problems from time to time. And so if we look at this problem, it says Laura is selling cookies to raise funds for a school club. Each cookie costs 50 cents. She has made enough ingredients to make 1,000 cookies. Here's our equation. M of C equals 0.5 C. C is your number of cookies, and M of C is the money made. So in this case, we can't really write out every possible value because we'd be writing 1,000 numbers, 1,001 really. So what we're going to do is we can write things as inequalities and a compound inequality. So we're thinking about the smallest number and the largest number. And so since domain is your input and C is our input here, C is the number of cookies. So we'll put a C here and we'll put less than symbols on either side saying that C is in between either of these two numbers. Now, this always has to be our smallest number. So what's the smallest amount of cookies we can make? Well, she really could make 0 cookies. She can't make negative cookies, but she could make 0. And she really actually could make 0, so I'm going to put an equal to sign there. And then what is the maximum amount of cookies she can make? Well, it says she's up to 1,000 from the word problem. And again, again, she can make up to 1,000, so I put my equal to. So what this is saying is that she can make any amount of cookies between 0, including 0, and up to 1,000, including 1,000, and every number in between. And we may want to write the whole numbers between. The reason we're writing the whole numbers between is because she probably can't sell part of a cookie, but she can sell 0, 1, 2, 3, 4. So those are the whole numbers between 0 and 1,000. Our range is going to be our money now, and the way we're going to do that is similar because we're going to have a lot of different possible amount of money we can make. So M is the money made, so I'm going to write M of C in the middle. I'm going to put my less than symbols on either side. So this is the smallest amount of money I make. So the smallest amount of money made is with the smallest amount of cookies made. So if she made 0 cookies, we'd put 0 in for the C here and get 0.5 times 0, which is 0. She'd make $0 if she made 0 cookies, and that's how much money she would actually make. Now the largest amount of money she'd make is if she sold 1,000 cookies. So we'd do 0.5 times 1,000. 0.5 times 1,000 is 500, and she would actually make $500 if she sold 1,000 cookies. So therefore we put the equal to. So this is saying the amount of money made would be in between 0 and $500, including each of those. So the word problems can get a little tricky. Key thing is the word problem will usually have enough information to give you your smallest and largest and your domain, but you're probably going to have to figure out the range based off an equation that they give you. All right, so then next we have graphs. And graphs can get a little tricky because depending on the type of graph is how you're going to write it out. So in this case, this is this is called a discrete graph when it's just the points. And we can, ultimately, since we only have 3 points, we can write those as ordered pairs on a table. So this is the point -3, 2. This is the point 1, -1. And this is the point 4, 0. There's no other points on that graph. It's just those 3. So therefore, we're going to write it. And since we were able to write it as a table, include all the points, we can write it just like we did on the other page. We write x equals -3, 1, and 4. In our range, same thing. We just write our y values, this is -2, guys. Sorry about that. -2, -1, and 0. All right, so if it's just the points, make it in a table and write it just like we did tables on the other side. If it's a graph where all the points are connected, that's where it gets a little trickier. We're going to have to write it as inequalities, kind of like we did the word problem. So the little trick you may want to know here and write this down is that you are going to be writing these points, these graphs that are continuous, points are connected, as inequalities like we did up here. And you're always going to have, for domain, you're always going to have your x in the middle. You're always going to have less than's on either side of that x. And it could be a less than or equal to, depending if it actually equals that value. And then your smallest x is always going to be on your left-hand side. Okay, so left is how far, smallest x is how far left your graph goes. And then your largest x is how far right your graph goes. That's going to be on your right-hand side of your inequality. Similar with the range, now you're talking about y values. You're always going to have less than symbols on either side of that y. It could be less than or equals to. And then you want your smallest y to come first, because your smallest number always comes first in these inequalities. So that's the smallest y's are how far down the graph goes. And then your largest y is going to go right here, which is how far up the graph goes. So I'll go over what that means right now. All right, so we're talking about our domain. So I'm going to put an x right away with less than symbols on either side. And since I want to know my smallest x first, that's going to go here. I want to know how far to the right my graph goes. So you can take a piece of paper or something and just slide it until you see how far to the left the graph goes. So I keep seeing the graph, keep seeing the graph, keep seeing the graph, keep seeing the graph. And all of a sudden the graph stops. But what do I have here? I have an arrow. So therefore that means it's going to keep going to the left forever. And the number that represents forever is infinity. And since it's going to the left or the negative side, we would write negative infinity. Now you can never equal infinity because infinity keeps going, so I'm not putting it equal to, it's just going to be less than. And then on my right hand side here, I'm going to see how my largest x, which is how far to the right the graph goes. So again, I can take a little piece of paper. How far to the right does this graph go? I keep seeing my graph, keep seeing my graph. All of a sudden right here, I stop seeing my graph, but I have arrows here. And what it tells me is that's going to keep going to the right and keep going down. So since it keeps going to the right, because I'm just worried about right or left for domain, it's going to keep going to the right forever. That means it would be positive infinity. So this domain, it goes from negative infinity to positive infinity. So it includes every single number. If it goes from negative infinity to positive infinity, we can also write this symbol x equals, and then we write like a fancy r. So you do like parallel lines and make that into an r. And that means all real numbers. So it's every single number in our number system. Okay, so either one of these is appropriate for this answer. You choose what you want to do. And then for our range, again, I'm going to put y down, less than symbol. And so we always need our smallest number to come first. Smallest y is how far down the graph goes. So I'm going to take my paper now and see how low the graph goes. So it keeps going down, keeps going down. I stop seeing the graph, but again, there were arrows here. So what that tells me is that it keeps going down forever. Forever is infinity, but since it's down, that's a negative direction, which would be negative infinity. And again, we can never equal infinity, so therefore notice these don't have equal signs. This slide is my largest y, or how far up the graph goes. So I take my paper, see how far up it goes. I see the graph, see the graph, see the graph. I stop seeing the graph right there. So that is the y value of 1, 2, 3. So the largest y value on this entire graph is 3. And since it actually does touch 3 there, I put an equal to. So this is saying every number between negative infinity up to and including 3. You could also just write it like this if you wanted to. Y is less than or equal to 3. Those are both the same thing. As we get into the next example, and the last example for this particular part, this is what we have when the points aren't connected. And this is a little tricky because you a lot of times have to either exclude numbers or write two separate inequalities. But for right now, we're gonna just get it started as we did before. I know domain is my x values, and since I know at least some of these points are connected, I can write inequalities right away. So the first thing I want to look at is how far to the left my graph goes. And my graph goes left forever. So I would say negative infinity here. And now as I see how far to the right I end up going, I see a little problem here because I see that hole, that open dot, which again means it's not equal to. So I got to keep that in mind. And then I keep going to the right, keep going to the right, and all of a sudden it's a whole different graph. But I do have a closed dot here, even though I have an open dot there. So I do have an x value of 1 at this part. So it's okay that this has a closed dot because x value of 1 still does work. And then it keeps going to the right forever and there's arrows. So every x value is included. All real numbers are included somewhere except one value. So I am going to put an infinity here because it does go right forever. But the one value and only one value that does not work on this graph for x values is this point right here, which is an x value of negative 2. So if it's just 1 or 2 points that don't work, you can write the inequality and then just write what we call an exception. Except x cannot equal, and in this case, x cannot equal negative 2. So our domain, or our possible x values, is every single x value, except the only x value that doesn't work is this negative 2. Even though there's a hole there, at 1, there is an x value of 1 on our graph somewhere right there. So again, the trick here is if you have just 1 or 2 numbers that don't work on your graph, write your inequality, write what the exception is. Now if we go to our our range, we're going to we know points are connected, so I can write it inequality, set my inequality up. And I'm going to say how far down my graph goes. And we can see it's going down forever. So I do negative infinity. It's not equal to, can never equal infinities. But now as I see how far up I'm going, notice I'm getting closer and closer. Oop, the graph stops there, which is a y value of 2. Negative 2. And notice there's an open dot there, so open dot means not equal to. So I would just leave that at this, saying, well, the y values are in between negative infinity and negative 2, not including negative 2. Or again, if you wanted to, you could just say y is less than negative 2. But there is still more graph up here. But they're not really connected like they were off for the domain. So I'm skipping y values here. I'm really skipping 2 blocks, but you have to think how many numbers are really in between 2 blocks. Well, if you include all the decimals, there's really an infinite amount of numbers. So I can't write an exception here because there's an infinite amount of numbers. Exceptions are only for like one single number or 2 numbers. Since there are an infinite amount of numbers between 0 and negative 2, I cannot write the exception. So the way I'm going to do this is I'm just going to write another inequality. So I'm just going to write the word and I'm going to set up another inequality for my y's. So now I'm thinking of this part. All right, well, how low does this part of the graph go? Well, it touches the y value of 0, so be careful. 0 is a value, and it's the y. And since it actually touches the y value of 0, I put 0. And then how far up my graph goes would stop there, which is 1, 2, 4. And even though there's an open dot at 4 here, all these values here have y values of 4, so I do want to put my equal to sign. So if you are, bottom line is if you're skipping just one number, write the exception. If you're skipping an infinite amount of numbers, write separate inequalities. All right. Next part is looking at, why don't you take a moment and work on your domain and range for these 3 graphs. Pause the video and try that. All right, taking a look at this, we can write this one as x equals all real numbers, or again, whichever way you write it, negative infinity to infinity, and the same with the range that goes down forever and up forever. So I can write y equals all real numbers, or negative infinity is less than y, which is less than infinity. Notice all these graphs are pretty much the same, it's just slightly different between them. So for graph 2 here, it's the same thing, it's just we have an open dot here. So what we're going to do is we can write that exception. There's just one single number that doesn't work. So I can write negative infinity less than x less than infinity, except x cannot equal, and that's an x value of 2. That point has an x value of 2. The range, again, we'd write the same thing. Y is less than, or negative infinity less than y, less than infinity. And again, we just write the exception because there's one number that doesn't work. In this case, it's a y value of 1. Y cannot equal 1. And then graph 3, those are just separate points. And so what we would do there, or what I would do, is I would make this into a table. So that's x value negative 1, 0, 1, 2, 3, and 4. So that's how I'd write my domain. X equals negative 1, 0, 1, 2, 3, and 4. Then my y values for that are 5, 3, negative 5, negative 3, negative 1, 1, 3, and 5. And so I just write those for my range. Y equals negative 5, negative 3, negative 1, 1, 3, 5. So again, since those weren't connected, I can't write those as an inequality. When you write the inequalities, it includes all the decimals, all the values in between. These points are not connected, so we're not including all those decimals in between, so we have to write it out like this. All right, what's the difference between these 3 graphs? It's just some vocabulary. So graph 1 is called a continuous graph, and that's when the points are connected. Okay, continuous graphs, points are connected, and you can see some other graphs. Anytime the points are all connected, you don't have to lift your pencil to draw the whole thing. It's continuous. Graph 2 that had the hole in it is called discontinuous. And discontinuous is when the points, there's a hole in the graph or you have to lift your pencil to finish it. So if you look here, this has a hole in it, it's discontinuous. Also that other example where there's somewhere that you just can't draw the whole thing without lifting your pencil. So I draw this graph. To get the rest of the graph, I'd have to lift my pencil and go here. So that's called discontinuous. And the last one is discrete. And this means the points are not connected. All right, you're going to practice some domain and range on the following pages. And good luck.